If you are new to the channel, then subscribe the channel and press the bell icon for further notification. Okay student, welcome you all to this new lecture in machine series. So today again we will be solving 5 questions starting from question number 136 to question number 140. Okay, then let's try to solve these questions. So in question number 136, a 3-phase 900 kVA 3 by root 3 start to delta to star 50 Hz transformer has a primary high voltage resistance per phase. This secondary resistance is given, iron loss is given, full load efficiency. So iron loss is given, you calculate copper loss because resistance are also given. You can do copper loss calculation primary side, secondary side separately, or you can convert all the resistance to primary side, then you calculate. That is also be done. In that case you will take care of only one current, that is primary current, because you are converting everything to primary. So if you convert everything to primary, total resistance R will be equal to primary plus you convert this one. Now what is the ratio here? It is delta to star, and this side it is 3, this side it is root 3 line voltage. So per phase it will be root 3 by 3. So it will be 3 is to root 3 by 3, that is 3 is to 1, that is your turn ratio is 3 is to 1. Because I told you per phase you calculate, per phase it is 3 because it is delta, whatever line it is phase voltage. Here line is root 3, so phase will be root 3 by 3, so that is 1. So it is 3 is to 1 ratio. So if you convert this 0.02, now will it be square into or divide? You see, because it is low voltage to high voltage you are going, so your resistance should also increase. So it should be multiplied by 3 square. So it will be 0.48. So if you know this ohm, everything is primary, so you multiplied by primary current. What will be primary current? It is per phase I am calculating. That has to be careful. So primary side you have to calculate I1 primary. Per phase. That you have to, because you are calculating per phase. Per phase loss you are calculating. Winding is in per phase, resistance is in per phase, not in line. The resistance are not connected in the line. This is on the winding, that is phase current. Through this winding phase current will flow. So you have to calculate phase current. So it will be 900 into 10 to the power 3 divided by 3 VP/IP. So for delta side, whatever VP, that is VL is VP. So it will be, it is 3 kV. So it is 3 into 10 to the power 3. So what I am using 3 VP/IP. So VP is here, 3 kV is VL, which is VP also because it is delta. So if you do this one, it will be 100. So what is your copper loss? Copper loss will be equal to 100 square. For 3 phase you have to multiply it by 3. Per phase it is 100 square I square R. So for 3 phase total copper loss will be 14.4 kilowatt. So your efficiency will be equal to, what is your output they are giving at unity power factor, operated at unity power factor, full load. So that means 900 kV into 1, unity power factor means 900 watt. So 900 kilowatt plus your iron loss is 10, copper loss is 14.4. So you will get it is 97.36%. Now if you come to question number 137, a 3-phase slip ring induction motor is fed from the rotor side. Stator winding is now short circuited. The frequency of the current flowing. Now the reverse thing you are doing. Normally what you give, supply you give to the primary, correspondingly secondary EMF is induced, and because secondary short circuited current flows, that magnetic flux follows that rotating magnetic field. Now the reverse happen. If you, that also reverse will also work. If you give supply to the rotor side, so rotor induced EMF due to electromagnetic induction, stator will get EMF because stator is 3 phase. So again it will, and you have already short circuited your stator. Therefore current will flow. The stator will give you a 3 phase rotating magnetic field. So your rotor will try to follow that one. So to nullify that due to Lenz's law, it will try to oppose the cause of its creation. So that's why it will rotate. So the same idea, if you give stator side supply, then what is the rotor frequency? Rotor induced EMF frequency is slip frequency. Because if it is, suppose it is rotating at 100 and it is rotating at 90. So at which the flux is cutting is at 10 RPM. So your frequency will be 10 because it, if both are rotating at 100, then they will be stationary to each other, no cut. So that is not possible. That's why induction motor cannot run at synchronous speed at all. So the gap through which it is rotating, that is the slip, that much EMF will be, your flux will be cut at that rate. That's why EMF will be generated at that rate. That's why it is slip frequency. So that is your option A. Now if you come to 138, skewing. What is skewing? If you see the rotor slots, if you have seen the rotor slot, the slots are not straight. It is always given a little tilted. So it is something like that. You have taken these slots and just you have twisted these slots. So these rotor slots are given little bit tilted. So there are a number of advantages of this one skewing. So one of the advantages is it take care of your slot harmonics. Skewing is used in induction motor in order to reduce the torque due to slot harmonics. Due to there may be a chance of locking, induction motor may not start at all. So due to that skewing, to avoid that one, we reduce due to the slot harmonics, that phenomena comes. So you remember in that way, you are tilting the slots for slot harmonics. So you can remember it this way, easy to remember. So 139, a 3-phase induction motor coupled with a pump operating at normal speed. If one of the line get disconnected, then motor stops. No, the motor will not stop. Why? If one phase get connected, then it is still 2 phases. Still it is polyphase. So if it is a polyphase, your rotating magnetic field is there. Induction motor is rotating due to this rotating magnetic field. Because it is still present, so motor will still continue to rotate. So that's why it is false. So 139 is false. If you come to 140, a 6-pole 50 Hz induction motor rotating at 1400 rpm. It is in which mode? Generator mode or motoring mode? So you calculate your synchronous speed, 120 into F by P. So if you see this one, it is 1000 rpm. And your rotor speed is greater than synchronous speed. That means it is at generation mode. So it is synchronous, it is working as an induction generator, not induction motor, because induction motor speed is always less than the synchronous speed. So that's why it is generator mode. Generator mode. That is your answer. If you like the video, then press the like button and please give your valuable comments in the comment section.